Okay, can you guys hear me?
Yep.
Okay, good. Um, just a couple things before we get started. Going over the notes. I did post your exam 3 to Newton. Okay. I did notice a few of you had started that. That was the old version from a past semester. So that got erased. A couple of you had completed it, so you're going to need to go in and redo it. It was over different stuff. So the test 3 that's up there now is valid for this semester, and it should be ready to go. I Now I forgot what I did. I think I included oxidation numbers on your practice exam, but they will not be on your test, like I told you guys. Couple other things. Um, I would like some feedback from you guys in terms of how you think this is going. I do have a freshman, son who's a freshman at USI, and he says pretty much no one's doing it this way. Uh, that people are doing like voiceover threads, and I just want your feedback in terms of, is that better for you? And then we get together during this time, or do you like doing it this way? And you can think about it. I will ask you again and probably put a notice on Blackboard in terms of, hey, give me feedback about this. Um, and we'll see how it goes from there. So I'm not going to change anything for this next exam, which would be essentially this lecture and Thursday's lecture, hopefully to test on Tuesday. But going forward after that, if you guys just want me to do a voiceover on my notes and then get together after that to discuss, I'm open to doing that. You got to tell me what works best for you. So kind of keep that in mind. Okay. Uh, Next week's lab, for those who have lab on Wednesday, tomorrow, that lab is up now. So again, hopefully kind of getting in the rhythm of things. You should try to do that before we get together. We will get together at 4. No, we will get together at 1 tomorrow, an hour into your lab, and discuss it. So again, the idea is you have done it or done as much as possible as you can with it before we get together. Okay. Okay. Any process questions or anything before we get going on what's going on? And the other thing I just wanted to tell you guys is my plan is to kind of go through the lecture today, and then I will stick around afterwards for questions you might have or that have come up. So kind of having that as an office hour sort of thing. I have not come up with a regular schedule, and my plan is to do that after Thursday's lecture as well. And I will probably do something for you guys on Friday as well. So whether that's at noon or at 5 or whatever, if you have strong feelings either way, just let me know. Okay.
Do you want us to ask the questions now or at the end?
So if you have questions on stuff we've covered up to now, wait till afterwards and then ask those questions. Certainly if you have questions as they come up when we're going through, ask them as they come up. Okay. I do try to remember to ask you guys if there's questions as we're going through, kind of like I do in class, or hopefully did in class. But I frankly don't know how good I am at doing that in this format. Did you guys catch that?
That sounds good.
It said my internet was unstable for a second. Okay. All right. Then switching over to our notes and kind of continuing on where we left off. Do you guys see the notes now? Are the notes up?
Yes.
Okay, thank you. I couldn't tell what my screen was doing. Okay. So basically what we had done at this point was we're starting to talk about solutions, reminding you when we make solutions, we express concentration in terms of molarity, which is moles of solute per liters of solution. And at this point, we had made a solution from starting with a solid, adding water to it to get it into solution and figuring out what the final concentration would be. The other possibility is to dilute a more concentrated solution. And for that, we use the formula M1V1 equals M2V2. And we did a problem like that here, which was similar to the problem you did in lab as well for the titration lab. Okay, and so we figured out for our problem that we needed 10 milliliters of 5 molar NaOH to get us 250 milliliters of 0.2 molar NaOH. Okay. So there's a couple different types of problems you're going to run into with this stuff. So I just kind of wanted to go through each of those with you. And so the first type of problem will be something like this. Okay. As it says, 1 milliliter of 1.25 molar HCl is diluted to a final volume of 400 milliliters. What is the molarity of the resulting solution? Okay. So again, this is an M1V1 equals M2V2 problem. And on these, you don't have to change your volume to liters. If you're using molarity as a conversion factor, again, it's moles per liter. Moles per liter times volume in liters gets you moles. But what we have here is, now what does matter is you do need to make sure you pair things up correctly. So my 1.25 molar does go with my 100 milliliters. And it says here diluted to a final volume of 400 milliliters. So that is one of your volumes. Okay, so setting that up into M1V1 equals M2V2, I'm going to call 1.25 molar M1. 100 milliliters is V1. M2 is my unknown. And 400 milliliters is my V2. All right. So rearranging and solving, basically what you're going to do, multiply these two together, divide both sides by 400 milliliters, and what you end up with is you end up with 0.313 molar HCl. Okay. Another way to think about it, to see if you're getting a reasonable answer, what did we do? We increased the volume by a factor of 4. We should decrease our concentration by a factor of 4. And this is, in fact, 1/4 of the original concentration. Okay, so for a problem like that, it's simple plug and chug, punch in as given. And the key here is it says you have a total final volume of 400 milliliters. So it is giving you the total final volume. All right. Now, another way you'll see that type of problem, it would be like this. That's a little blurry, but hopefully still readable. Let me check and see if someone else is trying to get in the room. No, I don't see anyone. So, okay. So another way you'll see that problem is something like this: 150 milliliters of 1.25 molar HCl is mixed with 225 milliliters of water. What is the molarity of the resulting solution? Okay. A lot of times on these, I like to say, if it helps you, draw a little picture of what's going on. Okay. So these almost look as good as the way I would write them out. Those are meant to be beakers. So in beaker 1, what do I have? I have 150 milliliters of 1.25 molar, whatever. Happens to be HCl, doesn't really matter what it is. Okay. To that, I'm going to add 225 milliliters of water. What can I say about the resulting solution? The resulting solution is going to have a volume of 150 plus 225, 375 milliliters. So that is stated differently than that first problem was. In the first problem, you were given this 375. Okay, so do be a little bit careful on the wording of these things. Okay. Now from there, it's, again, now it's M1V1 equals M2V2. M1 is 1.25. V1 is 150. M2 is our unknown. That's what we're solving for. V2 is the 375. Okay. So again, be careful on that because you guys see this 225 and you think it's got to go in there somewhere, and 225 actually never shows up in this. 225 plus 150 shows up as the 375. Okay. So again, 150 times 1.25 equals 375 times M2, dividing both sides by 375 milliliters. And you can see again here, obviously it cancels out over here, but you have 150 milliliters on top, milliliters on the bottom. Those units are going to cancel, which is why your volume units don't particularly matter for these types of problems specifically. Okay, and what you end up with is you end up with a molarity of 0.50 molar HCl. Okay, so that's just another way you'll state these problems. So the previous way, what do we have? We had initial concentration, initial volume, and we had total final volume. In this problem, what we've got is we've got initial concentration, initial volume, and additional volume. Okay, so we don't want additional volume, we want the total final volume to punch into M1V1 equals M2V2. Okay. All right, questions on that? Okay, so just be aware that that's another way you'll see a dilution problem. Now, for this, what we've got 150 milliliters of 1.25 molar HCl, and we're mixing it with 400 milliliters of 3 molar HCl. We want to know what's the molarity of the resulting solution. Okay. And I would ask you, is this a dilution problem? But it says right here, this is not a dilution problem. It's not a dilution problem because we are adding more stuff. We have HCl in the first beaker, we have HCl in the second beaker. Okay. So it's not a dilution. You can't use M1V1 equals M2V2. So what we're going to do is we're going to go back to more fundamentally what our definition is. And remembering what our definition of molarity is, it's moles per liter. So we need total moles of HCl in this thing. We need total volume of solution in this thing. Okay. So again, drawing a picture of what's going on. In beaker one, I have 150 milliliters of 1.25 molar HCl. In the second beaker, I have 400 milliliters of 3 molar HCl. All right. Now, kind of the example I like to use is if I have 5 grams of stuff in here and I have 10 grams of stuff in here, I will have 15 grams of stuff in total. So amounts of things are additive. Concentrations are not. If you have 1.25 molar here and 3 molar there, it's not going to be 4.5 molar. Okay, it's actually going to be somewhere in between 1.2 and 3 because 3 molar is going to concentrate this. 1.25 molar is going to dilute this. So it should be somewhere in between. So essentially what you want to do is you want to find the total moles and total volume. And we end up with that down here, just to kind of give you a preview of where we're going. Okay, so to get total moles, go back to using molarity as a conversion factor. I have 150 milliliters, that is 0.150 liters, times my concentration, 1.25 moles per liter. So this, again, comes from this. You're just expanding this out to use molarity as a conversion factor. Remember what 1.25 molar HCl means. It means you have 1.25 moles per 1 liter. Okay. And again, I've tried to stress this, moles per liter times volume in liters gets you 2 moles. All right. So when I crunch this calculation, 0.15 times 1.25 divided by 1, you get 0.1875 moles. That's the amount of moles of HCl in this beaker. Okay, so what about the second beaker? In the second beaker, you have 400 milliliters, which is 0.4 liters, times 3 moles per liter. So again, moles per liter times volume in liters gives you moles. And so what I can calculate is I can figure out in this second beaker, I have 1.2 moles of HCl. All right. So if I have 0.1875 moles of HCl in this beaker and 1.2 moles of HCl in this beaker, how do I get my total number of moles? Simply add them up, right? Okay. And that's where I come up with the 1.3875 moles. That's from the 0.1875 plus the 1.2. Gives me a total amount of stuff of 1.3875 moles. What else do I know? Definition of molarity is what? Moles per liter, right? So I have my moles. My total number of liters is 150 plus 400 milliliters gives me 550 milliliters. That is 0.550 liters. So when I take my total moles, divide by my total number of liters, I calculate that out, and I can't actually see that because I got this in the way. What I end up with is it looks like we got 2.52 molar solution for that thing, which should make sense because it's somewhere between the 1.25 and 3. We actually have more 3 molar than we have 1.25 molar, so you might suspect it should be closer to 3 than it is to 1.25, and it is. Okay. So again, not a dilution problem because you have both volumes, both concentrations. You're not just adding more solvent. So dilution doesn't work. You got to go back to fundamentals and figure out what's going on there. Okay.
Did you change it to liters because you knew you would have to use molarity to do moles over liters? Is that why you changed it to liters in the beginning?
Yes. So if you look at this here that I'm circling,
Mm-hmm.
if you have concentration, molarity, which is moles over liters times volume in liters, liters on top cancels liters on the bottom, you end up with the units of moles.
Okay.
So this time, yes, you do need to convert to liters to make that work. Okay. Questions on that? Okay. So that should familiarize yourself with solutions a little bit. The other thing we can do with solutions is what? We can have solutions involved in chemical reactions. So just kind of showing you how that would show up. We can say how many milliliters of 1.25 molar HCl are required to react with 1 gram of magnesium. Okay. So the first thing we would need to do is what? Figure out the equation. And I see that it's given here, okay? But kind of thinking about what's going on, you would have magnesium plus HCl gives you MgCl2. How do we know the formula of magnesium chloride is MgCl2? Someone make my day. All right, I'll make my own day. Magnesium is +2, chloride's -1. So again, when they combine, fundamentally, we know we should get MgCl2. Okay, plus what? We'll get H2, or we'll get hydrogen. Hydrogen's diatomic, so we get H2. And so that's what we get. So this is an example of a single displacement reaction. And what? Balancing it. To balance this thing, we just need to stick a 2 out in front of this HCl. Okay. So that's going to be important for our mole to mole conversion. All right. So if you look at this problem, think about what we have and what we need. All right. So we're looking for our volume of HCl. What do we have? We have grams of magnesium. How are those two things tied together? They're tied together by a chemical reaction. Okay. So thinking about your scheme, what do you know the most about? You know the most about magnesium. So my scheme would be from grams of magnesium go to what? Moles of magnesium. Okay. You guys should be comfortable with that. If you weren't until today, now's the time. Okay. Got to know this for your test. So from grams of magnesium, go to moles of magnesium. And how do I go from grams to moles? I use the molecular weight, or in this case, since it's just an element, it's the atomic weight, 24.3 grams of magnesium for every 1 mole of magnesium, getting that number off the periodic table. Now I have moles of magnesium. From moles of magnesium, I want to go to what?
Moles of HCl.
Moles of HCl. And how do I go from moles of one thing to moles of another thing? Use the coefficients in the balanced equation, right? This thing tells me there's 2 moles of HCl involved for every, no coefficient, so understood be 1 mole of magnesium. All right, so it's 2 moles of HCl for every 1 mole of magnesium. Again, coming from the balanced chemical equation. This would be one of those important conversion factors that we had written on the board over and over again, okay, that hopefully you're getting used to at this point, okay. Now, what am I looking for? I'm looking for volume of 1.25 molar HCl. So I have moles of HCl. Remember what 1.25 molar HCl means. It means I have 1.25 moles of HCl per 1 liter, okay? So in other words, this is a valid conversion factor for this particular solution. If that is a valid conversion factor, what else is a valid conversion factor? The reciprocal of that thing, right? Depending on what I have and what I want. Okay, so I have moles, I want liters. So the way you're going to see this now, using molarity as a conversion factor, I'm going to say for every 1 liter of HCl, there's 1.25 moles of HCl involved. Okay, so again, that is coming from this. This expanded out tells you this, 1.25 moles per 1 liter. And again, if that's a valid conversion factor, the reciprocal is a valid conversion factor. And in this case, I do want the reciprocal. I want the reciprocal because I want to end up with what? I'm circling it for you. Help me out.
Liters.
Liters, thank you. Okay. So I get, running through that, calculation-wise, I get 0.0658 liters. The problem specifically asked for milliliters. So hopefully you're comfortable doing that conversion. Move 3 places. Should have more milliliters than you have liters. So moving 3 places, I have 65.8 milliliters, which is what I have there. Okay. So this is tying in now solutions into chemical reactions. Okay. You should be comfortable with all these things at this point. Okay. From grams, go to moles. From moles of one thing, go to moles of another thing, using the coefficients in the balanced equation. And then here's the new one with solutions. From moles, I can go to liters, or from liters, I can go to moles by using molarity as a conversion factor expanded out. Okay. So again, I don't want to make these things sound simple. You guys are going to need to practice these, okay? But it's just a matter of taking what you start, going from where you start, figuring out where you need to end up with. And I didn't do it here, but write out your pathway if that helps you, at least for the first however many. Okay. All right. The next thing then is we can have a chemical reaction, and that chemical reaction can involve two solutions. Okay. So that's another problem you see here. How many milliliters of 1.10 molar H2SO4 are needed to react with 20 milliliters of 4 molar KOH? Okay. So first thing, write out your equation. H2SO4 is going to react with KOH. Hopefully you recognize that as an acid-base reaction. If you don't recognize that as an acid-base reaction, you'll get by recognizing it as a double displacement reaction. So the H combines with OH to give us water, and then K combines with SO4, and we get K2SO4, and again we get K2SO4 because potassium's +1, sulfate's -2, so we get K2SO4. All right. In order to balance that thing, I need to stick a 2 out in front of the H2O here. And that results in a 2 out in front of the KOH there, or you can get the 2 out in front of the KOH from this K2SO4. Doesn't matter. But eventually, you end up with this. Okay. So, whereas in the previous problem, I had grams of stuff, and I had to go to moles, and then convert to moles of something else. In this case, I have two solutions. So thinking about where you are and where you want to be, I need volume of H2SO4. I have volume, stick with me, I have volume and molarity of KOH. Help me out here. Given the volume and molarity of KOH, I can find
Moles.
moles, thank you. Okay, so I can get moles of KOH. All right, so doing that, this is what I've got here. I'm going to come off this thing for just a second just to make sure that whoever is wanting in here is in here. So hang on just a second. Okay. We'll come back. Okay. So this is how you do that, you guys. Again, what does molarity tell you? It tells you moles per liter. If I take moles per liter and multiply by my given volume in liters, you do need to be in liters. After this conversion, this number here, the 0.02 liters times 4 moles per liter, what am I going to have after that step in my process? I'll have moles, right? I'll have moles of KOH specifically, because liters on top, there it goes. Okay. Liters on top here cancels liters on the bottom. I have moles of KOH. Again, keeping in mind what I'm looking for volume of H2SO4. So from moles of KOH, go to moles of H2SO4. Again, using the coefficients in the balanced equation. That gets me to moles of H2SO4. What am I looking for? I'm looking for a volume. So I'm going to, right now I have moles. I need to get to volume, so I'm going to use my molarity as a conversion factor. What does your molarity tell you? Again, 1.10 moles of H2SO4 per 1 liter, or the way we're going to use it, there's 1 liter for every 1.10 moles of H2SO4. Okay. So that's your setup, kind of going through this in terms of units, liters on top, liters on the bottom. Moles of KOH on top, moles of KOH on the bottom. Moles of H2SO4 on top, moles of H2SO4 on the bottom. I end up with liters. I actually want milliliters. But so when I work that out, I get, I think it says 0.036. And it might be 0.0036. Did someone work that out? Let me run through it here real quick. Yeah, I get 0.0364 liters. So this should actually say 36.4 milliliters there. Okay. So do make that correction on here. Okay. This should be 36.4 milliliters, not 3.64. Okay. All right. So again, that's just using solutions and tying that in with chemical reactions and kind of tying everything together that we've done up to this point in terms of, well, tying in solutions with chemical reactions. Okay. Questions on that? All right, continuing on. I think I did this just as kind of a review problem. So again, using molarity as a conversion factor. If I have 0.350 molar NaCl, know what that tells me. It tells me there's 0.350 moles of NaCl per 1 liter, or in every 1 liter I have 0.350 moles. Okay, so I was just kind of using this as a review problem. This should be old stuff. I want to know what volume of 0.350 molar NaCl will contain 10 grams of NaCl. Okay, so your scheme here, you have grams of NaCl. From grams of NaCl, I can go to moles of NaCl. Okay, and again, that should be trivial at this point. Okay, and then tying that into a solution, once I have moles of NaCl, I can go to volume in liters by using molarity as a conversion factor. Again, what this 0.350 m NaCl means is you have 0.350 moles of NaCl for every 1 liter, or 1 liter contains 0.350 moles, depending on what you have and what you want. In this particular case, we would have moles of NaCl. We want volume, so I set it up this way. Okay. Crunching through, 0.488 liters is what you end up with. Okay. It didn't specify any sort of units, so you can just leave it as 0.488 liters, or you can convert that to 488 milliliters. It wouldn't matter. It didn't ask for a unit. Okay. All right. I'm going to call that good for solutions. Any questions on solutions? At least over the stuff we talked about today before we kind of move on? No? Okay. All right. Next thing then. Next thing we're going to do is talk about heat energy. Okay, so the first thing we're going to do is we're going to get through some definitions, and then we're going to talk about problems. Okay, so let me just check here a little bit. Okay. So I do want to talk about a few things that aren't on the notes. Heat is a form of energy. We have kinetic energy, which is energy of motion. We have internal energy, which is kind of chemical energy. We also have potential energy, which is potential energy can be converted to other forms of energy. Potential energy is based on position in a force field, like gravity, right? If I'm holding a ball up and I let go of it, that potential energy will be converted to kinetic energy. So you can convert from one form of energy to another. Okay. So an important thing to remember, keep in mind, is conservation of energy. Total energy remains constant. You can convert from one form to another. Okay. Now we're going to focus on heat energy. And so we can define heat as a type of energy that flows into or out of a system based on a difference in temperature between the system and its surroundings. Okay. Like it says, eventually thermal equilibrium or temperature equality is reached. Okay. In a simple kind of simplifying things, we can define two things then. We can talk about system, which is the substance or substances involved in the change being studied. And then the surroundings is everything around the system. Okay. So before I get into the examples that I went through in class, what I'm going to do is just use a very simple example with you. If you go to the store and buy soda, okay, buy the 12 pack. So kind of planning on drinking that soda for a while. What do you do with that soda once you get it home from the store? You stick it in the fridge, right? What happens to that soda when you put it in the fridge? It eventually reaches the same temperature as the fridge. Okay, so that's what we're talking about when we talk about heat. And what happens is you have a transfer of energy, heat exchanges, either goes into or comes out of the system until the temperature is the same inside as it is outside. In terms of like a fridge, which is an insulated system, those would be the surroundings. The system would be the can of soda, and eventually the system and the surroundings comes to the same temperature. Okay. All right. So just looking at another example of that, if I have a glass of hot coffee sitting in a room, okay, I just got it, it's nice and fresh, it's hot. The temperature of the coffee is high, the temperature of the room is low relative to each other, okay? So what happens if you leave the coffee sitting in the room? Okay, if you leave the room, what's going to happen is your cup of coffee is going to dissipate heat into the room or into the surroundings. So the coffee is going to lose energy. The room is going to gain energy. So in this case, our coffee would be our system, and our surroundings would be the room around the system. Okay. So what you'll notice is what? You'll notice the coffee gets cold. What else actually has to happen? The room has to warm up because the room is gaining energy. Now, since the room is so much bigger than the coffee, you're not going to go into that room and say, gosh, it's really hot in here, right? Because the surroundings are so much bigger than the system, you will notice the temperature difference in the system. You may or may not notice the temperature difference in the surroundings. Probably not for something this small. Okay. So a couple things to keep in mind. Like I said, in this example, since the temperature of the system is higher than the temperature of the surroundings, the system is going to lose energy. The surroundings, the room, is going to gain energy. Okay. Now, where that ties into what I just kind of talked to you a little bit about in terms of energy is what? What do we know is true? Do we gain energy or lose energy? And the answer is no. Okay. Specifically, the system can gain or lose. Specifically, the system can gain or lose, but we don't gain or lose energy. Total energy remains the same. All right. So what that means is if the coffee loses X amount of energy, I'm just going to say 1,000 joules. If we lost 1,000 joules, which is a unit of energy, if the coffee loses 1,000 joules, the room has to gain 1,000 joules, right? Because those two things have to be the same. Whatever energy is gained by one thing must be lost by another, because we don't change the total amount of energy. Okay. Anyway, this is kind of some real world stuff that you should be familiar with and should be able to grasp pretty easily. Kind of keep these things in mind as we're going through chemical examples, which might be a little more difficult to deal with. But what are we going to do? We're going to have chemical systems, and those chemical systems will either gain energy or lose energy. Okay, it's got to go somewhere. So let's see what's going on with that. All right. Now, we can define heat energy. What we're going to do is define heat energy as being defined by this variable Q. Okay. A couple other things to keep in mind when we talk about change in temperature. We talk about delta T. Delta T is final minus initial. Okay, so something's going to gain energy, something's going to lose energy. I actually do not like this statement here. Q of system equals Q of surroundings. One of those will be negative. Okay, so stick a negative sign out in front of one of them. It doesn't matter because they're actually opposite, like we saw earlier. I think I said what? The coffee lost 1,000 joules. The room must gain 1,000 joules. So there should be a negative sign here, or you can put absolute value brackets around it. Okay. Bottom line was 1,000 joules was involved. Something gained it, something lost it. Okay. A couple other things just in terms of defining energy here. Yeah. Somebody was having a bad day taking notes. Okay. A joule is not the same thing as a calorie. 1 calorie is equal to, should be 4.184 joules. And that's kilocalories, that's food calories. Actually 1 calorie, small calorie, is equal to 4.184 joules. Okay. So I'm gonna switch to the whiteboard for a second, actually, because I want you to see that. I'm gonna say that 1 calorie is equal to 4.184 joules. Okay, so kind of sticking abbreviations on there. 1 calorie, CAL, is equal to 4.184 joules. Okay. When we talk about things, we'll also often talk about kilojoules. Okay. So kilo is still the prefix, so it's 1,000 joules in a kilojoule. Okay. So they had the conversions on there wrong. This is what you need to know. Okay. Now, going back to this. How do we derive this in terms of energy? Okay. It actually kind of comes from kinetic energy. A joule in fundamental units, a joule is a kilogram meter squared per second squared. That makes sense in terms of kinetic energy because kinetic energy is 1/2 the mass of an object times its velocity squared. So if you have mass in kilograms and velocity in meters per second, when you punch into this, you're going to get kilogram meters squared per second squared. And we define that to be 1 joule. Okay. All right. Now, what do? We heat things up, okay? How much heat we need to add to heat up a certain object, a certain temperature, is defined by this specific heat. So this specific heat is a physical property of a substance, and we designate it with the abbreviation S. And so we can define specific heat to be the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay. So looking specifically at what that would look like, if you look up the specific heat of iron, it's 0.449 joules per gram degree Celsius. Okay, so these are very typical units on specific heat, because what is specific heat? It's the amount of energy, 0.449 joules, to heat up 1 gram of a substance by 1 degree Celsius. Okay, so like it says here, it takes 0.449 joules of energy to heat 1 gram of iron by 1 degree Celsius. Okay, now We don't always have 1 gram of iron. We don't always want to heat it by 1 degree Celsius. So to relate that to total heat, looking at this, let's say we want to know how much energy is required to raise the temperature of 12 grams of iron from 10 degrees Celsius to 40 degrees Celsius. Okay, so for that, we're going to use the equation Q equals Sm delta T. And for this, it's a simple punch-in. Okay, Q is heat. S is our specific heat. For iron, it would be given here. Okay, and for any problem you run into on Newton or anything on my exam or whatever, you don't need to know specific heat values. Don't worry about that at all. They would be given to you. Okay, so specific heat of iron times the mass of my iron, because what? Specific heat relates to 1 gram, 1 degree Celsius. So if I have 12 grams of iron, it's going to take me what? 12 times as much energy to get the same temperature change. So that's why we multiply it by that. And then multiply by delta T. What's delta T? I'm wanting to go from 10 to 40. So my delta T is 30 degrees Celsius. Positive 30 degrees Celsius. I want to increase it 30 degrees Celsius. All right. So again, Q equals Sm delta T. Take your S value, take your mass value, take your change in temperature value, run it through. Q equals Sm delta T, and Q for that thing equals 162 joules. So it would take 162 joules to raise the temperature of 12 grams of iron, 30 degrees Celsius. Okay. So for those of you who have lab tomorrow, you're going to be running into these calculations in your pre-lab and whatever. Okay. So again, have that done, and we'll get together at 1 and discuss it, and we can reiterate that if you have questions about it, which I kind of expect since we're just getting started on this stuff, and that's fine. All right. Any questions on, I'm going to call this kind of the definition stuff, kind of getting these fundamentals down? Anything on anything? Okay. All right. Next thing then, a 27.68 gram piece of metal at 400 Celsius is put into 1,000 grams of water at 20 degrees Celsius. The final temperature of both is 22.1 degrees Celsius. What is the specific heat of the metal? Okay. You're given here the specific heat for water. All right. So the important thing is you have 2 energy amounts here. What's going to happen to the metal? It's at 400 degrees Celsius. Is it going to heat up or cool down? Help me out. It cools, right? It cools down to 22.10 degrees Celsius. Your water is at 20 degrees Celsius. Does it heat up or cool down?
Heat up.
It heats up to 22.1.
Oh, I'm still unmuted.
Right. So something gains energy, something loses energy. The metal is losing energy, the water is gaining energy. What can you tell me about those energies? What has to be true?
They have to be constant at the end, like total energy.
Yes, so the energy gained by one thing will be equal to the energy lost by another thing, okay? So numerically, those 2 things have to be the same. All right, so what do we know? We're looking for our specific heat of the metal, okay? So we know everything about water. We know S for the water, we know M for the water, we know delta T of the water, okay? The other thing we know is the heat gained by the water will be equal to the heat lost by the metal. So this is where we get into that equation, and again, it was wrong prior. Q of the water equals negative Q of the metal. Okay. So for our water, what? Q equals SM delta T. Our Q is the 4.184 joules per gram degree Celsius that was given here. Our mass was 1,000 grams. And our change in temperature was, we went from 20 to 22.1. 2.1 degrees Celsius is our change in temperature. That is a positive change in temperature. All right, so crunching through that, Q equals SM delta T, 4.184 times 1,000 times 2.1, I get 86.4 joules. We're using sig figs a little bit there. I can live with it. Tell me what this number tells me. What happened to the water? Did it gain energy or lose energy? Help me. Please?
It gained energy.
Thank you. It gained energy, right? It gained 86.4 joules of energy. Okay. What must be true then? What must be true is something else must have lost 86.4 joules of energy. Okay. Why is that true? Because the conservation of energy tells us total energy doesn't change. So if the water gained 86.4 joules, something lost 86.4 joules. That happened to be the metal. So we're isolating our system here. You can think of our metal as being our system and the water being the surroundings. Okay. So now we know Q of the metal. We're looking for the S of the metal. We know the grams of the metal that was given in the problem. And we know the change in temperature of the metal. I went from 400 to 22.1, so my temperature went down by, I can't quite see that here, down by 377.9 degrees Celsius. So that's negative. That's negative. And then, I don't know if you can see what's going on here, but this basically got rewritten over here. And that shouldn't be a minus sign there, if that's what that looks like. So I have 8786.4, divide by 27.68, divide by negative 377.9. That's what that is. It's a negative sign, not a minus sign. Okay, so be careful of that. And what do I know? Working that out, I solve for the specific heat of the metal, which turns out to be 0.840 joules per gram degree Celsius. Okay. So that kind of ties everything in together in terms of using Q equals SM delta T and knowing the fact that if something gains energy, something else has to lose energy, the same amount of energy. All right. So we kind of saw that here. If Q of the water is that, Q of the metal is the opposite of that. Punching in the numbers for the metal, we were able to solve for S. This makes sense, and if you think about it, your specific heat will never be negative. It doesn't take a negative amount of energy to heat something up, so S should always be positive. Okay. Masses are always going to be positive. It's your change in temperatures that will be positive or negative. Okay. All right, questions on that? Are we good? Okay. Continuing on then. Now we're going to start talking about chemical systems, right? So tying this into reactions, we can relate this to what is known as heats of reactions. Like it says, some chemical reactions release heat, others absorb heat. Therefore, these reactions do have a certain amount of energy associated with them. Okay. So we call that thing a heat of reaction, where the heat of reaction is the value of Q required to return a system to a given temperature at the completion of a reaction. Okay. this Q value, like it says, is temperature dependent. All right. Now, just talking about this, I don't know if I addressed this later or not. Let me just take a sneak peek. I don't see it being on there. Okay. So in terms of chemical reactions, gaining heat or releasing heat, very typical chemical reaction. The most common type of chemical reaction are those that release heat. You can think about things, combustion reactions, burning stuff. You can burn methane, which is the main component of natural gas. You can use that heat to heat your home. You can burn propane to run a gas grill. You can burn gasoline to convert that into kinetic energy and drive your car down the street. Okay, so we burn stuff to give off heat, and we use that heat for various things. Okay, there are some chemical reactions, not that many, but some chemical reactions that take in heat. The best example of that is an ice pack used for athletics. Okay, so if you think about an ice pack used for athletics, usually you've got what? You've got a plastic container in a gel. You snap that plastic container, shake it up, and what happens to the gel? It gets cold, right? It gets cold because the chemical reaction that takes place when you snap that plastic container, usually that's a salt dissolving in there, that's grabbing in heat. It's grabbing in heat or taking in heat from the surroundings, which is that gel, so the gel then gets cold. Okay. Again, most chemical reactions will release heat, but there are some chemical reactions that do absorb heat, and therefore your surroundings would get cold. Okay. So kind of classifying those two things, okay, we can talk about two different types of systems. We can talk about something known as an exothermic process. And exothermic is what it says here, a chemical reaction or physical process in which energy is lost from the system to the surroundings. Okay, this is a key thing, and this causes a lot of confusion. Okay, when you're talking about something being exothermic or endothermic, you're talking about the system. Okay, so if you're losing energy from the system, where's it going? It's going to the surroundings, right? So it's kind of dissipating, going to the surroundings. If the system is losing heat, what has to be true? The surroundings is going to gain that heat. Okay. All right. So like it says here, for an exothermic process, the system's losing energy. So what does that mean? That means Q for the system is negative. Q for the surroundings is positive. How much energy is involved? I don't know. I don't care. But what I do know is it's the same amount, right? So something loses 10,000 joules, something else has to gain 10,000 joules. All right. Endothermic, pretty much the same thing, except it's the other way around. In an endothermic reaction, that is a chemical reaction or physical process in which energy is gained, so it comes in from the surroundings. So Q is positive for the system, Q is negative for the surroundings. Okay. So when we think about this, we're going to kind of summarize that. In an exothermic reaction, the surroundings will heat up. Heat is, I don't like that. Heat is absorbed. Heat is absorbed by the surroundings. Okay. Energy is being lost. Energy is being lost from the systems going to the surroundings. Okay. So energy is being lost. The system loses heat. Q is negative for an exothermic process. So what's exothermic? A combustion reaction or an ice pack?
Combustion reaction.
Thank you. It's a combustion reaction, right? The reaction's losing energy. It's losing energy to the surroundings, so the surroundings get hot. Okay, and that's kind of what causes confusion. Okay, so when you're thinking about these things, you got to be thinking about it in terms of the system. Endothermic reaction. What's going on? The surroundings cool off. So the surroundings lose heat. And the surroundings lose heat because what? The system is gaining heat. Energy is gained. The system gains energy. Okay, so Q for those things is positive. And so easiest question of the semester, is that the combustion reaction or is that the ice pack? That's the ice pack, right? So the system gains energy. It gains energy from the surroundings, which is that gel or whatever. Okay, so what you feel is you feel that thing getting cold. All right. So kind of keep those in mind. And again, review that thing, get it kind of straight in your head, the easiest way to think of it. And it's not easy because these terms cause confusion a lot of times. Okay. But you got to think about things in terms of the system, what's going on with the system to kind of keep straight whether something's endothermic or exothermic. All right. Okay. Let's look at a chemical reaction. All right. If I take hydrogen and I react it with oxygen and I make water, okay, what happens is I make water and I actually also make 572 kilojoules of energy. Okay, so I'm making 572 kilojoules of energy, or 572 kilojoules of energy is released, like it says. What does that mean? Is the reaction, there's the giveaway, right? Spoiler alert. Is the reaction endothermic or exothermic? It's exothermic, right? Does that make sense to you guys? It's exothermic because the reaction is giving off energy. Like it says, energy is released. Okay. How much energy? 572 kilojoules of energy is released. Okay. If it was taking in energy, it would be absorbed or gained or whatever. Okay. Now, from this information, what we can do is we can write what's called a thermochemical equation. A thermochemical equation is a chemical reaction and the amount of heat involved in that chemical reaction. So, like it says, it's a chemical equation for a reaction. It should include phase labels because those are important. So, for example, O2 get, well, let's use something a little more realistic. The heat involved when you form H2O liquid is different than the heat involved when you form H2O gas. The way to kind of convince yourself of that is if I go from H2O liquid to H2O gas, there is some additional energy involved. Okay, or less energy involved if I'm going the other way. Okay, so H2 plus O2 gives me 2H2O. There should be a 2 out in front of this. Okay, so that should be 2H2 plus O2 gives me 2H2O liquid. And Q for that process is negative 572 kilojoules. Why is it negative? Because 572 kilojoules of energy is what? Released or given off, so it's losing 572 kilojoules of energy. Or like it says in the problem, releasing 572 kilojoules of energy. So it's negative, and the negative sign tells you that that thing is exothermic, going back to this table up here. Okay. Now don't worry about this. This amount of energy, whatever it is for whatever reaction it is, would be given to you. We will actually figure out how to find that energy, but we'll get there. Okay, what I want you to understand at this point is that the quantity of heat obtained for a reaction depends on the amount of material involved. Okay, and hang on one second here. Okay. All right. So we have a thermochemical equation. And what we're going to do is kind of use that thermochemical equation. And here's just a different one. 4NH3 plus 3 O2s gives you 2 NO2s plus 6 H2Os. Delta H for that process is negative 1,267 kilojoules. Now, what these thermochemical equations allow you to do, so I think there's some information that wasn't written down. What I'm just going to tell you is Q is equal to delta H for a constant pressure process. And that's all we're going to worry about for this class is constant pressure processes. Okay, so there's a little bit of derivation that was involved in that. I'm going to tell you not to worry about it because I'm not going to ask you about it. The other thing that can happen is you can have, if you have a change in pressure, basically work can be done. If work is done, then total energy equals total energy, but some of the heat energy might be converted to work. Okay. So again, I'm going to tell you not to worry about that. This symbol delta H stands for change in enthalpy. For those of you who have lab tomorrow, that might ring a bell because you're doing a experiment on change in enthalpy. All right. Anyway, bottom line for this thing, okay? This is the amount of energy for this chemical reaction when you interpret this chemical reaction in terms of moles. So for example, what this says is there is negative 1,267 kilojoules of energy for every 4 moles of NH3, or for every 3 moles of O2, or for every 2 moles of NO2 made, or for every 6 moles of H2O made. Okay. So what it allows you to do, this is another important conversion factor. This allows you to relate energy to amount of substance in moles. Okay. So this is going to be another one of our important conversion factors. And we can do what with this? We can go from energy to moles of a substance, or from moles of a substance to amount of energy. And if that's a valid conversion factor, the reciprocal of that thing is a valid conversion factor as well, right? So I can say 4 moles for every negative 1,267 kilojoules. That's in terms of NH3. I can also state it in terms of O2 or N2 or H2O. Okay. So based on that, kind of the most fundamental question then is, I want to know how much heat is released from 1 mole of NH3 based on this equation. Okay. So my given amount is 1 mole of NH3. My equation tells me what? There's negative 1,267 kilojoules for every 4 moles of NH3. So that's coming from the coefficient in the balanced equation related to NH3. Okay, so I have 1 mole. This ties energy to amount of substance, either 4 of that, or 3 of that, or 2 of that, or 6 of that, depending on what you have and what you want. Okay, so if I have 1 mole of NH3, I know I get 1,267 kilojoules for every 4 moles of NH3. My amount of energy involved for my 1 mole is negative 316.8 kilojoules. Okay. Now, this is another place where I'm going to tell you you need to be careful of your wording and stuff like that. Because if you look at the question is how much heat is released. Okay. The negative sign tells you energy is released. Okay. So what do? You release 316.8 kilojoules of energy. The negative sign tells you it's released. Okay. So you don't release a negative 316. So the way you'll see these problems stated is it'll ask you exactly like it's stated here, how much heat is released. If it says how much heat is released, again, the negative sign tells you it's released, but you don't release a negative amount. You would say 316.8 kilojoules is released. Okay. All right. It could also say what's the change in energy involved. If it asks you what's the change in energy involved, then you say negative 316.8 kilojoules. Okay. Or what's delta H for this amount of substance. Okay. All right. So we kind of get into that. And the next one, an alternative way of asking that is what is delta H for this process? Then you leave the negative sign in there because delta H is negative 316.8 kilojoules. Okay. So be careful on wording. Okay. I'm just going to kind of give you a heads up on that. All right. Questions up till that point? Okay. So what I'm going to do is I'm going to call it good for today. I'm going to stop recording this. I'm going to get a drink because I'm dying. It's going to be soda. And then I'll come back. And if you guys are still around, I'll take questions, kind of treat it as an office hour or a review. Okay. Everyone good with that? Any questions before I'll stop recording here for a second?
What flavor soda?
Diet Dr. Pepper.
All right, that's all right. Thank you.
It might be in a Miller Lite can though.
It might. Nothing wrong with that.
Okay, you guys, I'll be back in a second as soon as I stop recording this thing. Let me get this figured out. Okay, stop share, stop